Ready for a next step of elimination by molecular, focusing on stereoselectivity. We're going to be drawing dashes and wedges to try to figure out major and minor products. All right, let's consider the dehydrohalogenation, right, removing a halogen of 3-bromopentane. So draw this with me. You have your reactant, your alkyl halide, with a 5-carbon chain, and at carbon number 3 is a bromine. So 3-bromopentane, an alkyl halide, the focus of our chapter, where the bromide is acting as the substrate, right? So this alkyl halide we refer to as the substrate. We have OET, ethoxide. Just so you hear its name, ethoxide, acting as a base. Sodium is the spectator. We talked about considering beta hydrogens. So I locate the carbons. Remember that this carbon attached to the leaving group is alpha. And so I can see in either direction, we have beta. And notice that really carbon 2 and 4 are equivalent carbons. In other words, I could number them from the other order and end up getting the same exact name. So they are equivalent carbons. That is still 3-bromopentane, ordering left to right or right to left. So when I think about 2 equivalent hydrogens, here's 2 hydrogens on this side, 2 hydrogens on this side. All 4 are equivalent. Let's just focus on one side. Notice that I have 2 possible hydrogens to abstract. And when I do so, 2 possible hydrogens on the beta carbon will lead to a cis-trans conformation. Here we had trans to pentene, and if the other hydrogen is taken, you would get cis to pentene, 2 stereoisomers. Now, in terms of predicting major and minor product, it's not proper to say Zaitsev and Hoffman because they are both di-substituted, but the trans configuration would be the major product. As we studied, trans is of lower energy than the cis conformation due to steric hindrance. So when we have 2 possible hydrogens on the beta, you will predict making both stereocenters, the cis as the major and the minor as the cis conformation is the minor, trans conformation is the major product. That occurs when the beta carbon has 2 hydrogens. You will make a cis and a trans conformation. But if the beta carbon, remember, has 2 hydrogens, 2 protons, the cis and trans were produced. What about this structure? Draw this with me on your paper. Remember that phenyl is an aromatic ring, and if you name it as a branch, a substituent branch, instead of naming it benzene, you name it phenyl. Let's draw this together. We have a carbon, carbon, and carbon number here, let's put bromine, knowing that that's the leaving group. And just kind of thinking how you're sketching that out, I'm going to just show with numbers that we're going to say the alpha carbon right here is attached to the bromine, attached to a terch butyl 1, 2, 3, 4. See how that's terch butyl? And then a wedge is a hydrogen. Here is the beta carbon attached to a phenyl. And I just want you to know that that's an aromatic ring when you see phenyl, attached to a methyl, attached to a hydrogen. Okay, what we're looking at in terms of beta positions. Here is my alpha carbon. The alpha carbon is attached to the leaving group. I'm interested in finding the beta carbons that contain hydrogen. Let's color code those blue. Here's a beta carbon. Here's a beta carbon. Those are both carbons 1 position away from the alpha. What's interesting now is this beta has no hydrogens. So no possible elimination will occur. Since that beta to the right of the alpha carbon has no hydrogens, that is not a possible source of elimination. That means we only are focusing on this beta. And I do see one hydrogen, and I'll highlight it in green as the beta hydrogen. With two beta carbons, one has no hydrogen for elimination. Therefore, the second has just one hydrogen, and that's only one stereoisomer for the product. This is the condition. The leaving group, which is on the alpha, and the beta hydrogen must be, and we'll say it's anti-periplanar. And we're going to write this over and over in the next several slides. That means they have to be in the same plane on opposite sides. And I can see that this is occurring in this particular example. Notice that the bromine is pointing up in the same plane as the carbon. The hydrogen is pointing down in the same plane as the carbon, and it meets the criteria of being able to undergo elimination reactions only when the beta hydrogen and the leaving group are anti-periplanar, same plane, opposite sides. And when this happens, let's kind of scroll down, kind of emphasize what we're looking at. We're in the same plane, the bromine and the hydrogen, same plane because they're both lines. They're not both wedges, they're not both dashes, but they're both in the same plane as the carbons. We'll have an elimination reaction occur. Remember the mechanism, NaOET, sodium ethoxide. Sodium ethoxide gives us a base, ETO, right? And that oxygen is the rich base seeking a proton. The proton that is abstracted is that proton in the beta position. That bond collapses and the leaving group leaves. Notice we need 3 arrows for an E2 mechanism. Proton transfer, followed by the collapse of a bond, followed by the leaving group leaving. So we did form the conjugate acid, don't forget that's there, and you did form the leaving group negative ion, and so that's where we would know sodium ends up to balance the charge. And what about the product of this elimination? We'll notice that the phenyl is a wedge, and the hydrogen is a wedge. They're going to end up on the same side. These were both wedges. That means they are cis to one another. Notice here you had, let me do purple, you had the tert-butyl as a dash, and you had the methyl as a dash. Those dashes are on the same side as one another as well, so that these end up being cis to one another as well. So what kind of conformation did we end up making? Thinking about the priorities across the double bond, phenyl is of higher priority than methyl, and you would see the tert-butyl of higher priority than the hydrogen. And this then looks like the opposite sides, so the only conformation to form would be the E stereoisomer. There is no E and Z because we only had one hydrogen to eliminate. Remember, the only time you'll get both the cis and the trans is if you have 2 beta hydrogens. And that was just saying 1, 2, 3, 4, 5. You would end up with a trans as the major, 1, 2, 3, 4, 5, and the cis as the minor. If there's 2 beta hydrogens. In this example, we only had 1 beta hydrogen. And therefore, we're not going to get both E and Z. We're going to get one or the other. And to determine if we get the E or the Z stereoisomer, we have to be sure that we place the leaving group and the hydrogen in the same plane, and they must be peri-coplanar. Bromine is on the alpha carbon, that's the leaving group, and the hydrogen on the beta carbon must be on opposite sides of the same plane. So what we're saying is, if, here's just another way of saying it, if bromine is a solid line, hydrogen must be a solid line. Or if you see this carbon and you have, let's say, the dash and a wedge system, if this bromine is on a wedge, this hydrogen has to be on a dash. That would also be anti-periplanar, opposite sides. So when we think about trying to work through anticoplanar, perhaps the Newman projections make the greatest sense. Notice that the bromine and the hydrogen are on opposite sides of the same plane in a Newman projection that is anticoplanar in a staggered position. If they are not in the same plane, if they're syn or the same side, notice this would be the eclipsed position. This is way too high of energy and therefore would not be the favored conformation. So the anticoplanar is a qualification for stereochemistry to have an elimination possible. Let's really dive into some good examples here. Practice, practice, practice. Dashes and wedges and Newman projections. So we're just saying that evidence suggests that the strict 180-degree angle, the opposite side, is not truly necessary, but just almost 180. So between 175, 179 bond angles are sufficient. That's why the term anti-periplanar is generally used instead of anti-coplanar. They have to be opposites of one another. So even though the E isomer is usually more stable, just think of that as we just said, trans is more stable than a cis conformation. But sometimes, just based on the location of the substituent groups, if we have no anti-periplanar hydrogen, you might not be able to make an E or a Z. That the stereochemistry is determined by the location of what hydrogen is available in the beta position. And I'm just going to practice with you several examples of how to predict stereochemistry. So let's predict the major and minor products for these E2 reactions with a strong base. You could just consider hydroxide or ethoxide. Any of those would be considered strong bases. First step, I want you to locate the beta carbons. To do so, I highlight the alpha carbon. And I know the beta carbons are one position away. Those are 2 beta carbons. Now on the beta carbon, I have hydrogens, but over here, there's no hydrogens, so no elimination is possible right there. That was supposed to be no elimination possible on this carbon because there's no hydrogen. We have 2 beta hydrogens. And when I have that situation, I'm going to be able to make the E and Z are both possible. Cis and trans, think of it that way. Alrighty, so let's count. I have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. On carbon 2, I have 2 methyl groups. And between carbon 3 and 4, we'll have a double bond. So remember the strong base? The strong base takes off a proton. This bond collapses and the leaving group leaves. There's your mechanism for elimination. So between carbon 3 and 4, we'll have a double bond. 1, 2, 3. This would be 2, 2 dimethyl. And at carbon number 1, 2, 3 to 4, yep, so at carbon number 3 of a 6 carbon chain, we have 2,2-dimethyl 3-hexene. That's the most substituted. Now let's take a peek at the stereochemistry. So in terms of the major product, we would look at that saying in terms of priority, the double bond, this side is the priority, this side is the priority. And so as you think about opposite sides, that is the E conformation. This would be the major product. But there would be a Z as well. And so the Z conformation becomes a cis conformation. So between carbon 1, 2, and then 3 to 4 is a straight line. Then we go up to 5, 6. This represents the cis conformation. So this is still 2,2-dimethyl and then 3-hexene. 1, 2, 3, 4, 5, 6 carbon chain, 2,2-dimethyl 3-hexene, but this would now be the Z conformation, which would be the minor product, since that is the more sterically hindered product. Now let's take a peek at letter B. Here we have our alpha carbon. I'll highlight in yellow. The alpha carbon is attached to the leaving group. The beta positions are 1 carbon away. Those are the beta positions. And right now, there's no hydrogen there, so there's no elimination possible in that direction. The beta position here has a hydrogen, even though it's not shown. I can see a hydrogen as a wedge and the methyl group coming up here as the dash. So this means that yes, we can have an elimination, but right now the stereochemistry is not correct because it is not anti, it is syn. And remember what I'm saying, if the halogen is a wedge, and it is, then the hydrogen must be a dash. And right now it's also a wedge. So right now this would be syn. We need it to be anti. So that means we have to rotate the bond. And to rotate the bond, I'm going to rotate it in this direction. Let's just really focus on what I'm saying. I'm going to draw this particular carbon. And I want to rotate that with you very slowly. I'm going to highlight this one in green and make sure this is the one you see I'm examining. Right now, this carbon has a methyl group as a dash, a hydrogen as a wedge. In the same plane is an ethyl group. And going down in the next same plane, you see this chlorine. But I'm just focusing on the green carbon. My goal is to twist this in this direction, and to do that, you're just rotating the bond. And I want to rotate so that everything moves one spot over. So I'm rotating the bond, and I'm going to do so to rotate the hydrogen over one. So let's just redraw. This is so critical to be able to redraw. I'm going to just let you know I'm redrawing that green carbon already after rotating. And remember, sigma bonds, these are all single bonds, are free to rotate. So I'm not changing anything at all about the conformation. I'm just rotating to make sure the hydrogen is in the back. So the hydrogen converts to the dash. The ethyl converts to the wedge. The carbon chain still is there. That's the chlorine. And now down here in the same plane is the methyl group. The methyl went to the same plane. Hydrogen, the ethyl group went to the wedge. Hydrogen over here is the dash. We just twisted and rotated the molecule. Now, if you want to build that molecule, it might be so helpful to be able to twist the bond. When you rotate a sigma bond, just move all the priorities one position over. Hydrogen was a wedge, goes to the dash. The methyl was a dash, goes to the same plane. The ethyl was in the same plane, it's now on the wedge. Everybody just switched over one. But look what happened. The chlorine is now the wedge, and the hydrogen is now the dash. That's perfect to predict the product. In other words, we need to have them be pericoplanar, right? Empty coplanar. So let's just redraw cleanly so you can see. I had 1, 2, 3, and this guy's here. That's that carbon. Down here, this is our wedge out to chlorine. Then coming down here now is a methyl group. Coming up here is your ethyl group. That's a wedge. And the dash is the hydrogen. Now we are anti-periplanar. So the base abstracts the proton. So let's just say it's hydroxide, whatever it might be. The base abstracts that proton. This bond collapses and the leaving group leaves. What kind of conformation are we going to make? Remember that it'll be a double bond in there. So carbon 1, 2, 3, 4, 5, 6 carbons in the longest, oops. 1, 2, 3, I got it, 4, 5, 6. The ethyl group is now pointing up. So the double bond going here, what's on top? We have this carbon with 3 carbon branches coming off, and there's this hydrogen there. We have the ethyl group coming up, and there's the methyl group coming down. So this configuration shows this particular group is pointing up, this group still pointing up, the hydrogen pointing down. That was the dash here. And then, of course, the fourth group would be the methyl group pointing down. So did we end up with a cis? No, we have to use E and Z. What is our configuration? Well, the highest priority is this guy. Highest priority is this guy. That's the same side. That's the Z conformation. There is not a mixture of E and Z, but only the Z conformation, which we would see is the least stable based on energy, but that is what we led to based on twisting our bonds. So the Z conformation is the only possible answer. This takes practice, my friends. When there's just one hydrogen in the beta position, it must be anti-periplanar in order to predict if an E or a Z conformation comes out. Let's keep practicing. Here's a next homework question. What are the major and minor products for the E2 elimination bimolecular? So first step, I want you to find the alpha carbon. Next door to each direction will be the beta carbons. Of course, this has no hydrogens, so I have 2 beta hydrogens. And when I have 2 beta hydrogens, I will have a mixture of product. You'll have a major and a minor product, and both really the cis-trans conformation. So as I think about redrawing the product, 1, 2, 3, 4 carbon chain off of the phenyl group, So here's our aromatic ring. We come out to that beta carbon. We would go up, back down, up. And the double bond would now be between those carbons. Now, this would be the major product. And since this is a opposite side, it would be the E conformation. What about the minor product? Redraw your phenyl group, go down to carbon 3, but now all of a sudden we need to make it the cis or the Z conformation. So I have to go back up and then lead out. Here we would have the Z conformation as the minor product. And so both hydrogens on the beta position gave us a mixture of a major and a minor product, but I do create both stereoisomers. The E and the Z conformer are both possible. Let's look at letter B. Letter B, I can find that beta carbon. There's no hydrogens there. So that means I can only focus on the hydrogen that's in position next door to the halogen. This is the alpha, this is the beta. Unfortunately, the hydrogen is in a syn position. They're both dashes. We need them to be anti. We need one to be a dash, one to be a wedge. That means we have to rotate the bond. So I'm going to redraw, give myself a little room down here, and I'm just redrawing letter B. And if it's all right, I'm going to let pH stand for the phenyl group. That's going to how I'd be representing there. So I have a phenyl leading to a carbon that leads out with a wedge to a methyl group, leads to a dash with a hydrogen, leads here to the carbon that has the dash. So I know that that's the wedge, and I lead down to a tert-butyl group. Right now, I don't have them anti-periplanar. They're both in the same plane. So just to stress, if the leaving group is a dash, the hydrogen next door must be a wedge. It must be in order for the reaction to occur correctly. So I've got to rotate this bond. All right, to rotate it, I'm going to spin all three of those around. So where I see, I'm just redrawing just so you can see what I'm focusing on. This stuff stays the same, alrighty, but what I've done is twisted. So down here, where it was the phenyl, oh, I twisted the wrong way, Linda. Oops. Moment in time, please. I'm so sorry. I twisted the wrong way. I need the hydrogen to go to the wedge. I made it go to the line. So that won't take me but a minute. Let's redraw. Going up, we said in the same plane was the phenyl. Going down was the hydrogen. This was the methyl. And then for some reason I switched clockwise when I really wanted to go counterclockwise. I want my twist to go this way. Just rotate those so that we have the hydrogen coming out on the wedge. So now up here would be the methyl group on the same line. The dash has turned into the phenyl, and the wedge is now our hydrogen. And we've accomplished the stereochemistry we need, where the bromine is the dash, the hydrogen is the wedge. So the mechanism, we would have a strong base abstracting this proton. This bond collapses and the leaving group leaves. And when that happens, we form a double bond. The double bond leads between the two carbons, the alpha beta carbon. Pointing up was the methyl group. Pointing down was the phenyl group, the aromatic ring. On the opposite side, here's the hydrogen, and here's the tert-butyl functional group there. So based on priorities, what did we make? Well, the phenyl is the higher priority on this carbon, and the tert-butyl would be highest priority on that carbon, And so that's the same side. This is the Z conformation as the only possible stereoisomer. Letter B forms a Z isomer, only one. What about letter C? Oh, I like what I see. Do you see it? If the methyl group is the dash, the hydrogen already is the wedge, we don't need to spin. And since it's already meeting the criteria of being anti-periplanar, the beta hydrogen is in the correct position. We'll eliminate the proton. Here is the beta carbon. Pointing down will be the hydrogen, leading in a double bond. And then pointing down here would be the butoxide group. Let me draw that better. And of course, this would be a hydrogen there. So with this conformation, that it was already meeting the criteria of being anti-periplanar, the halogen, which is the leaving group, is a dash. The hydrogen is a wedge. Perfect. And so this hydrogen gets plucked off by the base, which I should draw the arrow this way. O negative reaches for this proton, that bond collapses, and the leaving group leaves. So between our carbon, alpha beta carbon, is now a double bond. The priorities would have our phenyl group on this side of the pi bond, the tert-butyl on this side of the pi bond, and therefore that's the opposite. We've made the E conformation as the only possible stereoisomer. So letter B led us to the Z conformer, but letter C led us to the E conformer, and that is just really based on the wedges and dashes of the beta carbon. We cannot practice enough. Trust me, that spinning of the carbon bond, make sure that you practice that. This is also true for cyclohexanes when they undergo elimination reactions. The bond of the leaving group must be anti-periplanar to the beta hydrogen. To be anti-periplanar, the leaving group must be axial. And I realized that we learned that the equatorial bond is more stable, but you'll see that if it's in the equatorial position, there is no anti-periplanar hydrogens at all. So if chlorine is on an equatorial bond, no elimination possible. If I see that this hydrogen pointing down, this chlorine pointing up, both are on axial bonds, this meets the criteria to be eliminated, forming an alkene. So axial bonds only. Now in a round structure, like a cyclic structure, to be anti-periplanar, if the leaving group is a wedge, you need the hydrogen to be on a dash. So with this example, both of these hydrogens are able to be eliminated. And so if you do, they both meet that stereochemistry, you could form cyclohexene, and which is exactly equivalent to that cyclohexene. So there's just one unique product. Eliminating either beta hydrogens gives me cyclohexene. They are equivalent. Over on this structure, if I have a cyclohexene and my leaving group is a wedge, next door to it I have a methyl group, and this beta hydrogen is also a wedge, this will be not possible because it's not correctly aligned as an anti-periplanar hydrogen. So it will not undergo elimination. As a matter of fact, it's just this hydrogen in the beta position that can possibly be eliminated. Not this one, but yes to this one based on the stereoselectivity of anti-periplanar. Whoops. There, thank you. So when this undergoes elimination, the only possible product The methyl group is still here. I'll put that as a dash. You see that does not change. The leaving group left. And so that would be carbon 1, 2, 3. That would be 3-methyl cyclohexene. 3-methyl cyclohexene, the only possible answer for that elimination. So we would just verify this is the only product, and this would be not observed because that hydrogen was not in the proper position. And one more to consider. If next door in beta positions of a cyclohexane, if both hydrogens are in the wrong position, so the leaving group is a wedge, each beta hydrogen is a wedge, this will not undergo elimination. And remember, with cyclic structures, there is no possibility of twisting the bond. So therefore, when we had a straight chain, we were able to twist a bond. But when it's in a cyclic structure, you can't twist a ring. They're connected to both ends. So it's either in the correct structure or not. No twisting is a possible solution. I wouldn't mind just keep working a few more examples. So practice, practice, practice. So if you're still with me, I'm going to keep working some sample homework problems. Here we have a compound where I have 1, 2, 3, 4, 5 carbons in the longest carbon chain. I would name this 2-bromo, 3-methyl, pentane. Just a little practice with nomenclature never hurts. So elimination. In an elimination reaction, we locate the alpha carbon and we find in either direction the beta carbons and look to see what possible configurations we have for elimination. I can see that the beta hydrogens at position 1 are indeed available for elimination. That when in the presence of this strong base, I can abstract a proton, that bond collapses, and the leaving group leaves. One possible answer is making the double bond between carbon 1 and 2, and the methyl group still at carbon 3. So one possible product would be 3-methyl, 1-pentene. But this is the least substituted alkene. And so I would predict this is actually the minor product. What about next door here at carbon 3, we see that we have a wedge of a hydrogen. So that means we can have an elimination reaction occur. It's just not in the correct position yet. So I have to twist the bond. So just thinking that through, here's the carbon, and right now, let's just kind of keep in mind what's happening. Here's the carbon that's attached to, oops, I didn't really draw that in the right direction. Let's highlight this carbon so you can keep track of which one I'm drawing. I'm going to color it blue. So here's the blue carbon, and next door to it is the green carbon. Alrighty. And so when I twist, I just twist one. So carbon that's green is still attached to the bromine, still has a methyl group on this side, but it's coming down to the carbon I highlighted in blue. And as it sits now, we have a dash leading to a methyl. We have a wedge coming out to a hydrogen, and in the same plane is an ethyl group. We want to rotate to become anti-periplanar. That means the hydrogen needs to go to the dash, the methyl will go to the line, and the line will go to the wedge. There's our spin. Let's redraw. We had a methyl leading up to the green carbon, who has the wedge going up to the leaving group, coming down to the blue carbon. Alrighty, let me just make sure you see that the green carbon is still the same, blue carbon still the same, but I've twisted the location to where now the dash has become the hydrogen. The straight line is the methyl group, and the wedge is leading out to the ethyl group. There we have the correct stereochemistry for elimination. So the strong bond, the strong base, let's say it's OET, ethoxide, will abstract the beta hydrogen. That bond collapses and the leaving group leaves. What do we form? Well, the carbon-to-carbon double bond forms, and as you predict, make sure you keep track of this guy is the blue one, this guy is the green one, just to help you see how things are attached. Coming up would be the hydrogen. Coming down would be the methyl on the green carbon. Going up would be a methyl group here, and coming down would be the ethyl group here. That's a 2-carbon chain. I'll call that ethyl. So now when I think about drawing, we had a carbon, 1, 2, 3, 4, 5 carbon chain. Between carbon 1 and carbon 2 is a double bond, and it went down to form an ethyl group. How about labeling? Is this E or Z? Well, the highest priority in the first carbon there is this methyl group. Highest priority in the next one would be the ethyl group. That's the same side. So this is the Z conformation. And just thinking about following through on naming that, the double bond gets the priority. At carbon number 3 is a methyl group. And at carbon number 2 is a double bond in a 5-carbon chain. That was the Z isomer of 3-methyl-2-pentene. The trick here is just practicing twisting the bonds to make sure you get the conformer correct. Is it E or Z? Before you make that decision, make sure that they're anti-periplanar. The leaving group and the beta hydrogen must be anti-periplanar. I'll do another one if you'd still like to hear more practice. If you're ready to try them on your own, great. If you want to hear more practice, here I am. Here is the next set of homework. It's number 25 on your skill builders. I notice that I have an alpha carbon. The alpha is attached to the leaving group. I can see that I have a beta carbon here and a beta carbon here. So one of the products I can see would form from elimination in a least substituted, and I can just quickly draw those. That hardly takes thought at all. When I lead up, down, up, the isopropyl group stayed the same, and the double bond formed between carbon 1 and carbon 2. This, however, is going to be a minor product because it's the least substituted, but it is still possible. What about the major product? Let's find the major product, which would be the Zaitsev product, which would be the most substituted, but I need to know if it's an E or a Z conformation. And right now, I have the hydrogen in the beta position on the wedge, and it needs to be on the dash. So we have to redraw that, spinning the priorities. Leave the alpha carbon alone and just spin the priorities on your beta carbon. I'm going to just come down here so you can see. This is your beta carbon. Right now I have a wedge on the hydrogen. I have a dash on this isopropyl group leading down to the chlorine like this. And then down here is your phenyl group. And I'm just going to write pH, and you'll know that that aromatic phenyl. So as we spin, the spinning keeps those two carbons, the beta and alpha, are in the same plane, but I'm spinning the other 3 attachments. So the dashes and wedges stay in the same line. You're just spinning what's attached to them. The phenyl was in the same line, same plane. It moved to the wedge. The hydrogen was a wedge. It moved to the dash. The isopropyl was a dash. It moved to the same line. There's your isopropyl group. So that gives us the conformation of being anti-periplanar. So now when we think of the mechanism, here we have a base. The base abstracts the proton. This bond collapses, and the leaving group leaves. The double bond is a position where carbon to carbon, which were the beta alpha carbon, are now in a double bond. Pointing up is the phenyl, pointing down is your isopropyl. Pointing down is your carbon. Oops, I'm sorry. That carbon has its methyl group up, and therefore that's your hydrogen. So what have we made? Phenyl is of higher priority. Carbon is of higher priority. Our conformation is the Z, the Zane side. The Z conformation would be the only other product, and it would be the major product, the Zaitsev. I'll do another. How about letter B? Letter B gives us cyclohexane with two wedges. Let me just redraw. We have a wedge on the bromine and a wedge on the methyl. Yep, okay. In the presence of a small base. So you know what's nice? I see that I have two products, right? Because I would have a hydrogen in this direction and a hydrogen that's in the correct spatial arrangement already. No twisting. So yes, this is possible. And yes, this is possible. So one possibility for an elimination reaction would to place the double bond here and your methyl group here, and the methyl group still here and the double bond here. The most substituted will be the major product. That's your Zaitsev. The minor product is the least substituted, and that's your Hoffman example. We have been doing a lot of stereochemistry. When you come back in your next lesson, we'll discuss elimination and nucleophilic substitution in the same section for unimolecular multi-step mechanisms. Good work, everyone. Come on back when ready.